So let's go ahead and start where we left off last time. So remember, we're in 8.3 and 8.4. Which is about polar coordinates. Last time we converted points. So you take a point in rectangular and we converted that to polar form. And then also we took a point in polar form and we converted that into rectangular. And the conversions we had came from the right triangle, and they were this. X is equal to R times cosine theta. Y is equal to R times sine theta. R squared equals X squared plus Y squared. And then tangent of theta is equal to Y over X. Okay. And these all just came from, well, this one's the Pythagorean theorem, the other three come from SOHCAHTOA on the right triangle. Okay. These two, if you're given R and theta, these are the ones used to find X and Y. If you're given X and Y and asked to find R and theta, we'll use these two. And remember, the interesting thing about this one is that if you are given X and Y, if you're using this and finding inverse tan, remember inverse tan gives you an angle in either quadrant 1 or quadrant 4. So if you know your point starts in quadrant 2 or starts in quadrant 3, the way to figure out the angle is to just get whatever the calculator gives you and add pi to it, right? And that's what we had done last time. So just as a reminder, we've done a couple of these, but let's do another. Let's say we have a rectangular point, and we're going to try to find a polar point. So if you have the rectangular point 3, 8, how do I get the corresponding polar point? And then let's do -3, -8. And let's try to find the corresponding polar point. Okay. We did this last time, so I'll kind of go through it pretty quickly. If I'm trying to find the R squared is equal to X squared plus Y squared. So since I have this X and this Y, I can simply take the square root, and just like last time, we'll assume the R has to be positive. And we'll assume the angle has to be between -pi/2 and 3pi/2. So square root of 3 squared plus 8 squared is about 8.54. So the polar point is going to have an R value of approximately 8.54. Then I say, well, since 3/8 is in the first quadrant, theta is simply going to be the inverse tangent of 8/3. That's about 1.21 radians. Remember, make sure every time in polar coordinates, we're going to be dealing with theta in radians. Okay, polar coordinates always in radians. So that's the essence of it. Now on this one, we're going to do a very similar thing. R squared is going to be -3 squared plus -8 squared. So that's again about 8.54. We're using a positive R in this case. But in this case, -3, -8 is in the third quadrant. So when I go to find my angle, we're going to take inverse tan. In this case, -8 over -3. And then we're going to add pi to that because I know inverse tan is going to give me something in either the first or fourth quadrant. And so you get an angle which is approximately 4.35. So once again, if the point is either in the first quadrant or in the fourth quadrant, we're just going to use inverse tan because that's quadrants that my calculator output is going to give me. If it's in the third quadrant or the second quadrant, then we use inverse tan and then add pi to it. And we saw the reasons for that last time. So these are all point conversions. We're converting points in rectangular to points in polar right now. But we've also, last time, converted points in polar to points in rectangular. And that's a little bit easier. I don't have to worry about which quadrant I'm in. I can just type things in this way, right? Using these first two. So in essence, we've converted a lot of points. Well, today, what we're going to do is we're going to convert equations to equations. Equations in polar form to equations in rectangular form, and equations in rectangular form to equations in polar form. All right? And it turns out we use these exact same conversions. Right? The same conversions that we used to convert points to points, now we convert equations. All right. So let's say we have a rectangular equation. Let's take x squared plus y squared equals 36. And I want to convert that into polar. Now, there's actually a couple of ways you can do this. If you're ever stuck in rectangular and have to convert to polar, you can always just replace every x you see with r cosine theta and every y you see with r sine theta. So that's one option, right? However, in this case, there's actually a more clever option because we actually have x squared plus y squared. And if you ever have x squared plus y squared, then you can use this conversion. Or if you ever have y over x, you can use this conversion. So in this case, if I were to convert to polar, probably the easiest thing is to say, oh, I have an x squared plus y squared, so let's replace that with r squared. So we got r squared is equal to 36. And usually, we take a positive square root of both sides. By the way, remember in polar, I can assume the r is positive, so, right? If r was negative, I just use whatever angle I have plus pi. And then I get the positive corresponding point, so, or the same point with positive r. So r equals 6. And this kind of highlights why sometimes in polar, well, let me rephrase this. This highlights why certain things in polar are nicer than in rectangular. This is a fairly complicated equation to deal with. It's just the equation of a circle centered at the origin. We've seen this before, but in polar, notice how easy it is. It's just r equals 6. And if you're algebraically dealing with this equation versus this equation, this one's easier to deal with. Obviously, not every time are we going to get that sort of simplification. Let's say we have a rectangular equation, y equals 3x plus 4. That's a pretty that's a pretty basic equation. It's a straight line, obviously.
When you're converting from rectangular to polar, do you want to be using degrees or
Radians.
radians?
Yep. Yeah, so we're always, in polar, we always use radians. I shouldn't say always, but most always.
Okay.
We use radians. In this class, we'll always use radians for polar. And there's a really good reason for that. And that is if you go into calculus, you learn some things about derivatives and integration. And all of those rules that you learn about derivatives and integration are rules for derivatives and integration in radian form. If you do it in degree, then it throws everything off.
Okay.
So since the goal is to hopefully go on to the next class, which is calculus, we'll do everything in radians. So think radians. All right, so let's convert to polar. Now, there's no y over x here that I can easily get. There's no x squared plus y squared. So I'm basically forced into replacing every x I see with r cosine theta and every y I see with r sine theta. So when I convert to polar, r sine theta replaces the y, and r cosine theta replaces the x. Now, this is a fine enough equation. This is an equation in polar. But just like when we deal with rectangular equations, a lot of times we solve for y. A lot of times we get y equals. In polar form, a lot of times we solve for r. So we get r equals a function in theta. And if I want to do that, then I would subtract 3r times cosine theta from both sides. And then I would factor out my r. And then I would divide both sides by this sine theta minus 3 times cosine theta. So I get r equals 4 divided by sine theta minus 3 cosine theta. The sine theta minus 3 cosine theta is all in the denominator. So if I did solve for r in this case, it looked like that. Good. I don't know what this is doing. This is supposed to be on, but. Excuse me. For some reason, my overhead projector is not on. Shoot. Well, I'm just gonna talk through it then. So you might say, well, obviously in rectangular, this might be an easier equation to deal with compared to dealing with this in polar, right? And it probably is for most applications. This one is probably easier to have a rectangular than a polar. But I do want to mention about kind of just solving for R. If you grab your calculator and go into your mode, you're going to see a line that allows you to switch between function, parametric, and polar. Function is referring to the normal rectangular equations. If you switch it to polar, then you're dealing with R's and thetas. So if you switch your mode to polar and then go to your graph by hitting y equals, what you'll notice is that the inputs look like R equals and then, blank. So if I wanted to graph this, I have R equals already in there. So I just do 4 divided by, and then in parentheses, sine theta minus 3 cosine theta. And you might ask, well, where do you get a theta from? You just use your variable key, which is right next to the alpha. So you just hit sine variable key minus 3 times cosine of your variable key. And then if I just do a normal zoom, like standard zoom, you'll see that you get this equation. You'll see that you get a straight line. That would look like y equals 3x plus 4. Does that work? So you can graph this on your calculator. I was going to show you that, but for some reason the projector is not linked up, not allowing me to. Show my calculator. You can also do that on Desmos too. This one is linked up already. Sure. So if I do R equals 4 over, and then here's the deal. When you want a theta to come up, you type in the word theta, T-H-E-T-A. And then it'll come up. Minus 3, and then cosine, and then T-H-E-T-A. And as soon as I hit that last letter, it does that. Now, Desmos kind of automatically knows that if you're dealing with R and theta, then you're dealing with polar, and it assumes you're dealing with radians. So there it is. Is that right? Desmos can also handle the ones that aren't solved for R. So if you did r sine theta equals 3 cosine theta plus 4. Oh, 3r cosine theta, sorry. Notice you get that line too. So Desmos can graph even if it's not solved for r. Your calculator, you have to solve it for r to be able to graph it. Okay. Does that make sense? So that's the deal. Now, putting everything on one side and then factoring out the r, that's not the only way you can solve for r. There's a number of other ways you can solve for r as well. Let's do one of those. Let's say we have a parabola, vertex at the origin, so x is equal to, let's just do 20 times y squared. Again, I don't have the x squared plus y squared. I don't have the y over x. So I'm just going to just replace every x I see with r times cosine theta, and every y I see with r times sine of theta. So I get that. When I square that right side, I get 20 times r squared times sine squared. In this case, since everything is being multiplied, the way to get r by itself is to first divide both sides by r. As long as r is not 0, that's okay to do. That's going to cancel out one copy of r from the numerator and just leave me with one copy of r in the problem. And then to get r by itself, I divide by 20 times sine squared of theta on both sides. So I get cosine of theta divided by 20 times sine squared of theta is equal to r, or r is equal to cosine theta divided by 20 times sine squared theta. So that's solving that equation for r. So going from rectangular to polar, if I see an x squared plus a y squared, I use it. If I see a y over x, I might use that. But I always have this fallback option. If I have an x, I can just replace it with r cosine theta. If I have a y, I can replace it with an r sine theta. and do algebraic manipulation until we solve for R. By the way, some equations in polar are not easy to solve for R. So it's sometimes impossible to solve for R in polar. Just like sometimes if you're solving for Y in rectangular, it's impossible or near impossible. I'm going to give you ones that you can solve for R in, but again, in general, you're not going to always be able to solve for R. Now let's go the other way. Let's take a polar equation and convert into rectangular. Now, this avenue is sometimes a little bit tricky. I guess we could use the fallback option of every time I see an R, replace it with the square root of x squared plus y squared. And every time I see a theta, replace it with inverse tangent of y over x. But that's usually not very efficient. Okay. I'd actually rather replace r cosine theta with an x. I'd rather have an r sine theta and be able to replace that with a y. And I'd rather have x squared plus y squared and be able to replace that with an r squared. Or y over x and replace it with a tangent. But these two in particular are nicer to deal with. So what I would like to do is I would like to manipulate my equation so I get r times sine or r times cosine. In this case, that's pretty straightforward. In this case, all I have to do is multiply both sides by cosine of theta. And when I do that, I get r times cosine of theta is equal to 5. And now I can replace r cosine theta with my variable x. So r equals 5 divided by cosine of theta, that's actually just the rectangular equation x equals 5. Okay. Now, this is not the only technique that we can do. That's the tricky part. Let's say we had r equals, actually, let's just do this. R equals 11. I look at these conversions and I say it would have been nice to have cosine attached to the r. It would have been nice to have sine attached to the r. It would have been nice to have an r squared. If I multiply both sides by cosine, it's going to mess up the right-hand side. If I multiply both sides by sine, it's going to mess up the right-hand side. So in this case, it's best to try to get an r squared. So I'm going to square both sides. And I can do that without messing things up if I assume that r is positive. So in this case, squaring both sides gave me r squared is equal to 121. And now I can replace that r squared with this conversion of x squared plus y squared. Sometimes people try to solve things for y, but you do not have to. There's no need to solve for either x or y here. We all hopefully can see that that's a circle centered at the origin with radius 11. Any questions about that? Pretty straightforward. So let's do another one. Let's take r equals 3 times sine theta. Now, in the first one, remember, I like to get the r and the sine together or the r and the cosine together. The first one, we're using cosine. Cosine was in the denominator, so I can multiply both sides by cosine. I can't multiply both sides by sine here because that would give me sine squared on the right-hand side. So the trick for this one, because I like r sine theta, I'm actually going to multiply both sides by an r. What that's going to give me on the left-hand side is r squared. And on the right-hand side, I'm going to rewrite that as r times sine theta. And now I can say, well, r sine theta, I know what I can do. I can replace that with a y. And on the other side, I have an r squared, so I can replace that with x squared plus y squared. So I replace the r squared with x squared plus y squared. Replace the r sine theta with y. And that's it. That's the whole thing. So that's another trick we can use, right? So one trick is algebraically multiply both sides by a cosine or a sine. Another trick is multiply both sides by r. We can have, there's lots and lots and lots of other tricks as well. Okay. Any questions about this technique? Let me do one other conversion. Let's take sine of 2 theta is equal to 15. And we want to convert that into rectangular. Well, in my argument, these have to be sine of theta itself, not sine of 2 theta, right? So multiplying by r is not going to do that anything there. What I have to do here is basically go back to one of my double angle identities. For sine of 2 theta. And the double angle identity says if you have sine of 2 theta, that's going to be the same as 2 times sine theta times cosine theta. Now I have a sine theta, and I have a cosine theta, but I don't have the r in front of those. So what I'm going to do from here is I'm going to multiply both sides by r squared. If I do that, I can attach one r to my sine theta, one r to my cosine theta, and then on the right-hand side, I'd have 15 times r squared. Now I can replace r sine theta with a y. I can replace r cosine theta with an x. And I can replace r squared with x squared plus y squared. That work? All right. Oh, I guess depends if I'm I didn't put parentheses there. So if I don't put parentheses, then I have to distribute the 15. If I put parentheses, I can leave just the 15 out front. By the way, when you're typing your answer, typing things in like this is fine. But I do want to mention that whenever you multiply a variable times a letter, like a variable times another variable, make sure you put a multiplication symbol in between. Because if you put in x, y, it thinks that you're treating that like as a word, like the XY. And the same thing is true if you put in R cosine theta, you have to put a multiplication in here. Otherwise, it thinks you're trying to introduce a new variable called R cosine. That's just the way the programming works. So if you don't put any multiplication symbols in between your variables, it thinks you want it to do a new variable called XY. Or it thinks you want a new variable called RCOS. Like you're just naming it that. So make sure you put a multiplication symbol in between any variables. Now, if it's a numerical value like 15, if you did 15 COS, it's going to know that you're applying multiplication there. Or if you're doing 15 times Y, it knows that you're applying multiplication there. But if you do XY, it thinks, what's this new word XY that you're using? Right? So that's the idea. Is that right? Understanding polar to rectangular? Anybody feel comfortable doing that? Polar to rectangular equations. Oh, shoot. Now, sorry, I was going to get something out from the book.
So you would just write it in decimals as the 2xy equals the 15 x
Squared plus 15y squared. Yeah, so in Moodle, if you're writing your answer, you write it like this, but you do have to make sure you put a multiplication symbol in between the x and y,
right.
or else that's all I was saying.
Mhm.
So you write it just like this, but make sure you put a multiplication symbol here so it doesn't think xy
Yeah.
is some sort of a new word.
I just wanted to make sure that that's like the finish, like that's the answer that you're looking for.
Yes, this is the finished answer. On these, you do not have to solve for y or solve for x or anything like that. Okay. Let's go through this for a second. If I were to graph these types of things, well, I don't even know if this one would be an interesting graph. This one probably would not be at all. I don't think there's any real numbers that work here. But if you're to graph any polar equation, this was probably a bad example. But if you're to graph any polar equation, you could graph it by plotting points. So if we're to graph polar equations, one way that we could graph is by plotting points. So you just get a bunch of points and then you keep figuring out what they are. You know, what points I get, and then connect the dots. That's how we first learned how to graph in rectangular. You just plot a bunch of points and look for a pattern. Okay. So, option one plot points and look for pattern. The trouble with that is that it takes a long time if your graph is fairly complicated. All right. So if your graph is fairly complicated, that method could take a while for you to figure out the pattern. Option 2 would be to convert to rectangular and then knowing equations in rectangular, knowing what their graphs look like, we could hopefully graph the rectangular version. That would have been really nice on a couple of our conversion ones we just did. When we had R equals, what was it, 5 over cosine theta, and then we multiplied both sides by cosine theta, and we got x equals 5. Well, knowing that x equals 5 is just a vertical line, we could have easily graphed that. So converting to rectangular and then graphing the rectangular version, that's a good option too. However, as we saw, like in the last example, we had sine 2 theta equals 15. We got this really crazy graph, or we got this really crazy expression in rectangular. So rectangular is not always easy to graph. And so what we're going to do, mostly in this class, is we're going to look at option 3. And then that is use technology in polar mode. Whether that's our graphing calculator or whether that's Desmos. I was going to use the graphing calculator. I don't know what's wrong with the hookup from our projector, but it is what it is. So we use technology in polar mode. And this is what I was dealing with before. If you simply change the mode on the TI-84 to polar, well, everything comes out as R's and thetas now. So you go Y equals R equal, Y equals button. All of the graphs are now polar solved for R. Okay. So for instance, if we ask, let's graph R equals 3. Well, R equals 3, when you actually graph it, is a circle centered at the origin. With radius 3. And you can graph that in on your calculator. If you just type that into Desmos, it looks like a really nice circle. One of the things about typing things in on your calculator is you have to understand the screen stretch, because your calculator screen is further left and right, has more space left and right than it does up and down. If you type R is equal to 3 on your calculator and you're using the standard zoom, it might look like an ellipse because it's stretched. Your calculator stretches out the y-axis further than it stretches out the x. I'm sorry, I flipped the flopos. Stretches out the x-axis more than it does the y-axis. Excuse me. In standard mode. By the way, if you want that to be fixed, if you go to your zoom and you do zoom square, what it does is it makes each measurement on the y-axis of 1 unit the same as each measurement on the x-axis of 1 unit. So if you did zoom square, you get a circle. If you do zoom standard, you get a circle, but it's stretched out, so it kind of looks like almost like an ellipse. How about this? What if you did theta equals, let's say, pi over 3? Well, it turns out Desmos is not going to recognize that in polar. What you're asking to do. Okay. Anybody know what this actually is? Go for it.
Is it something to do with because you don't have an R, so you don't have a distance, you just have a random angle?
Yeah, so angle, you don't have a distance. So it's kind of like when we have x equals a number or y equals a number, you end up saying, well, what's the other one? Let's say I had y equals 5. If I had y equals 5, I graph that. Every point which has y value of 5 is graphed. Now for this one, technology doesn't treat it very well. But what it actually is it's the set of all points that has some R value and then pi over 3 as the theta. If you think about what that is, that's a line through the origin at angle pi over 3. And in this case, technically, when you do something like this, you have to allow both positive R's and negative R's. So you get a line through the origin. All right. By the way, in rectangular, if we graph x is equal to a number or y is equal to a number, we get vertical lines and horizontal lines, right? Now what we're seeing is in polar, if we're graphing r is equal to a number, I'm getting circles. If I'm graphing theta equals a number, I'm getting lines through the origin. Now, the reason I point that out is because in my normal rectangular grid, my rectangular grid is broken up into vertical and horizontal lines, right? So it's broken up into vertical and horizontal lines. That's our rectangular grid. If we go to a polar grid, a polar grid is going to look like, this is just a regular polar grid, circles around the origin, so concentric circles around the origin, and lines through the origin. So if you graph on a polar grid, or a rectangular grid, it looks like vertical and horizontal lines. If you graph on a polar grid, it looks like lines through the origin and concentric circles. That makes sense? And that's for this reason. Again, x equals a number, y equals a number, give you vertical and horizontal lines. R equals a number in polar, gives you these circles whose center is the origin. And theta equals a number, gives you lines through the origin. Okay. I wonder, no, doesn't graph on polar either. Sad. Now we're going to look at some other graphs as well. And some of these other graphs, I'm just going to look at from things from the book. So this is the book. And it's wanting you to graph a bunch of different things. So there's a lot of different types of graphs, whoops, that we're going to look at. There it is. I don't care if you use the rectangular grid or the polar grid to do this, but I'll graph some of the things that are in the book. If I do R equals cosine of theta, notice that I get a circle whose point is at, where one point is at the origin. One point is at the rectangular point, 1, 0. So it's a circle that goes from the origin out to 1. If I put a number in front of that, like a 6, now it's a circle from the origin to 6. If I make that number a negative, flips on the other side. If I change that cosine to a sine, well, then we're talking about going along the y-axis rather than going along the x-axis. So you get one loop, basically. All right? So that's a way to get circles which pass through the origin. And if you're reading along in the book, sometimes the origin is called the pole, P-O-L-E. So if you ever see that language, that's what that language is. Okay. What are some other types of things we can do? Well, what if we have 6 plus sine of theta, or 6 plus 7 sine of theta? Well, that's different, isn't it? 6 plus 7 sine of theta gives us this shape. It starts out up here looking kind of like a circle. But as it goes further down, it comes in and it loops, goes out. If I change this number, I just get a bigger inner loop. If I change it to a really small number, there's a big difference, I get a really big inner loop. Does that make sense? So the coefficients here are telling you about the loops. Now, here we did 6 plus sine theta. What if 6 plus 7 sine theta? What if I start changing that 7 to a smaller number? What if I do 6 plus 6 sine theta? Then all of a sudden my inner loop goes away. It just comes up, touches the origin, and goes back out. Or 6 plus 5 sine of theta. Then it indents a little bit, but it doesn't get all the way up to the origin. Or 6 plus 3 sine of theta. It indents, but just barely indents. Okay? And in the book, wow, this is so big. In the book, you can see all the different versions of this. But some of them are A plus B cosine theta, A minus B cosine theta, A plus B sine theta, A minus B sine theta. These are all known as cardioids. All right? And if, oh, what does this say? If A and B are the exact same, then that cardioid comes in and touches the origin and goes back around. If we have A and B, which are different, then it kind of matters which one is bigger. If the constant, the A here, is bigger in absolute value than the B, then we're not going to have an inner loop. We're going to have an indentation. And sometimes, if the ratio is too large, you don't even really see the indentation. That makes sense. There's no real visible indentation there. So we get an indentation, a visual indentation, when the ratio between A and B is between 1 and 2. Okay. We call these one loop lemicons when we have this one loop because we just have an indentation essentially. By the way, this is actually not specifically an English term, so I'm probably mispronouncing it. I always call them lemicons or limacons. But they look like, why are they called that? They look like a lima bean, right? That's the idea. They have that bean shape when they have the indentation. So that's a one loop lemicon. Here is an inner loop lemicon. This is what I originally had. This happens when the coefficient in front of the sine or the coefficient in front of the cosine is bigger. And again, whether it's pointing left, right, up, or down, that kind of matters on the positive, negative structure of the coefficients. But if the coefficient in absolute value in front of the cosine or the sine is bigger than the constant, then we get an inner loop. Okay. And that's what I was trying to show you here. If I change that to a 7, we get an inner loop. If I change that to an 8, get an inner loop, because 8's bigger than 6, right? If you subtract instead of add, it just kind of flips it around. That makes sense? If you put cosine instead of sine, it just moves things along the x-axis rather than the y-axis. What are some other interesting and well-known polar graphs? Well, one of them is simply r equals theta. Notice what r equals theta does. It gives us a spiral. By the way, this is letting theta go from 0 to 12 pi. So notice after 12 pi, it just shuts off. If you let it go just to 2 pi, then it's not going to have as much of a spiral. If you let it go to 24 pi, then it's going to have an even bigger spiral, right? So that's 0 to there. Let's say we just did 4 pi. We'll zoom in on this. If you let it go to negative 4 pi, it's going to spiral the other direction. You see that? That's hard to maybe tell. Spirals the other direction with negatives. Okay. Let's do another one. R equals theta. 0, 4 pi. There you go. See how it's just mirror images of each other. These are both blue. Let me change these are both red. Let me change this one to a blue. So I'm getting a positive spiral in blue. And when I say positive, I mean positive values, negative spiral in red. Okay. Interestingly enough. So there's a spiral in one direction, There's a spiral in the other direction. Is that right? So r equals theta gives you a spiral. What do you think r equals, let's say, cosine of 3 theta is going to do? Any guesses? What did cosine of theta give us? Cosine of theta just gave us one circle, right? Cosine of 3 theta gave us an object with 3 loops instead of just 1. Let's think about what happens now. What do you think is going to happen if I do 5 theta? We're going to get 5 loops, right? There it is. And if I did cosine of 7 theta, I get 7 loops. These are often called flowers or rose graphs. There's a bunch of different names for them. I just call them flowers. The book, not that one, there you go, calls them rose curves. And you see, here's a rose curve with 3 loops. It breaks it up into odd and even. Here's why. Every time we have an odd number in there, like 7, I get 7 petals on my rose curve. If I did 9, I get 9 petals. So you might think, well, what happens if I do 2? It turns out you don't get 2 petals, you get 4. And if I did 4 theta in there, instead of getting 4 petals, I actually get 8. And if I did 6, you can see the pattern, I'm going to get 12 petals. If you do sine, you also get 12 petals, but notice it's like almost rotated a little bit. Okay. If I do cosine, I get the blue graph. Sine, I get the red. Okay. Same idea though. The reason for that has to do with the zeros and how the zeros happen at pi and pi over 2, and so evens affect that in one way and odds don't. Odd numbers don't. So when you have an odd number in there, you get exactly that many petals. When you get an even number in there, you get double that number of petals. And you can put any coefficient you want in front of these, like let's put a 6 in front. All that does is stretches out how big the petals are. Now the petals are length 6 if you measure from end to end. Does that make sense? So those are rose curves. All right. I already mentioned spirals. So now we see we have circles, which are essentially rose curves with just one petal, right? In some sense. We have cardioids. Those are the ones where we're indented. We have interloop lemicons, rose curves, spirals, and there's obviously other curves as well. But it is interesting into seeing what you can plot. Now, I just want to point out something. that should be fairly obvious. And that is, in rectangular coordinates, this would not be a function. This would be a really, really messy looking function in rectangular coordinates if we had to like create it. We have cosine of 5 theta. We probably have to use a bunch of trig identities and mess around a lot with it to try to get it into rectangular. And it's definitely not going to be a rectangular function because it fails the vertical line test. But in polar form, this is, R is a function of theta. So being a function in polar form has nothing to do with the vertical line test. Being a function in polar form, technically, actually has to do with these lines through the origins. If the line through the origin just passes through one, then we're good to go. Does that make sense? But it doesn't matter. That's not the important part. And you can get messier and messier polar functions and see how things work out. I'm not going to do that. For this class, it's sufficient just to say, I know what these things look like. I know the cardioid. I know the lemicon with an indentation. I know the lemicon with a loop. I know what a rose curve looks like. I know what a spiral looks like. By the way, that's sometimes called the Archimedes spiral. Just as that type of spiral, R equals theta. And we're looking at this with polar coordinates just because sometimes, and by sometimes, this would be one example. These rose curves are much, much easier to deal with in polar than they would be in rectangular form. So when you go into calculus and you want to take derivatives, and you say, well, should I do it in polar or rectangular? This one's going to be an easy, let's use polar. Okay. Y equals 3x plus 4, that equation we saw earlier, that's going to be much easier in rectangular to manipulate. So that's kind of why we go with 2 different coordinate systems. Sometimes one's much easier to deal with than the other. All right, so that's enough polar material. We're going to skip 8.5. 8.5 is not something we typically go over. And that's polar form with complex numbers. That's not something we deal with. But we do want to deal with parametric equations and their graphs. Okay. So this is yet another system. But it is basically related very closely with the rectangular system. So far in the rectangular system, we have a single equation giving us the relationship between x and y. All right? With parametric, we introduce a new variable. Usually, that variable is t. On occasion, it's also going to be theta. That's somewhat confusing, I know that. But usually it's going to be t. All right? And we create two equations. One to generate the x value. And the other generates the y value. So that means a set or a parametric equations always come in pairs. So for example, here's a parametric equation, or sometimes people say equations. X is equal to 3t plus 1, and y is equal to t squared minus 6. Sometimes people put the little set brackets to denote that these two are a pair of equations, pair of parametric equations that belong together. Sometimes people put just the set brackets on the left. Sometimes people won't include the set brackets. Sometimes people include the set brackets around both, right? So it all means the same thing. This is a pair of equations that are working in unison. One giving you the x value and the other giving you the y value. Right? So in this example, if I were to plot points, we would create a table with 3 columns. And we put a bunch of t values in. So maybe I put -3, -1, 0, 1, 3, I'll do 5, I'll do those. So if I wanted to plot points, I put a bunch of t values in. When I put those t values in here, this first equation, I get my corresponding x values. So let me plug that in. If I plug in -3 into this equation, I get an x value of -8. If I put in -1 into this equation, I get an x value of -2, I believe. If I put a 0 into this equation, I get an x value of 1. You see what I'm doing? I'm just plugging in, just like I normally would. Plug in 1, you get a 4 for your x value. Plug in 3, you get a 10 for your x value. Plug in 5, you get 14. No, I'm sorry, 16 for your x value. Subtract. Then to find the y value, you use the other equation, the t squared minus 6. You plug in -3 into that. 3 squared minus 6 is a positive 3. If I plug in a -1 into that, -1 squared minus 6 is -5. If I plug in a 0 into that, you get a -6. If I plug in a 1, I get a -5 again. If I plug in a 3, I get 3 squared minus 6 is a positive 3 again. If I plug in a 5, I get 25 squared minus 6. That's 19, I believe. I'm quoting on that, but. Okay. And so if you're plotting points, the points that I have, one of them is going to be -8, 3. So I get the point, maybe I should have put that, but -8, 3. Then I get the point -2, -5. Then I get to point 1, -6. Then I get to point 4, -5. Then I get to point 10, 3. Then I get 16, 19, which is way out. side of my graph. Now, if you came up with other points, which you could, just use different t values, right? Just use lots and lots of different t values. What you would end up seeing is that this graph is actually a parabola whose vertex is 1, -6. That makes sense? So if you wanted to plot points, you could. You just plug in a bunch of t values. Now you might say, why would we ever do this? Why would we use parametric equations when we already know equations for parabolas? We already know equations for parabolas. Well, just like with the polar, sometimes parametric are going to be easier to deal with. Also, there's one other advantage of parametrics. So why use parametrics? All right, one answer, sometimes they're easier to deal with. So sometimes it's easier to get X and Y individually than at the same time. So that's one reason. The second reason is that if we are dealing in the real world, like in a physics scenario, this parabola might mean something. And introducing a new variable or a new parameter allows us to use this parameter as a time variable. So not only are we asking about where is the point, but at what time are we at this location? Does that make sense? So sometimes it's beneficial to have a new variable or a new parameter for t, I should say, for instance, when t represents time. And the xy is a location. So think about like an orbital path of a satellite. You say, oh, that's the path of the satellite, but when's it going to be at all of those places? So the path is important, but when it's there is also important.
Alternatively, could you view it or use this as like a third dimension on the graph too? Or not quite?
So that's a good observation. Now we've introduced a new variable. You could absolutely use this as a third dimension. Typically though, if you want to use a third dimension, we add another variable z, and then we have 3 dimensions and then a time aspect. Does that make sense? So that's the more commonplace. So, but yes, you could. Yes, you could see this in 3 dimensions, but usually if we're thinking in 3-dimensional space, then we use a new variable called z, and then we can use our time, like when we're talking about orbiting satellites, let's say. And then we have 3 dimensions where the satellite's orbiting in. And we use a time variable to say, where is it at this particular moment? But yes, we could. All right. So those are the 2 main reasons why we like to use parametric equations. Now, in terms of what we're going to do in this class, and things of that nature, well, one of the things that we're going to do is we're going to use conversions. Once again, we can go back and forth from parametrics to rectangulars, and there's some interesting ways that a rectangular equation can look in parametric forms. All right? So let's convert So we're going to be converting parametric to rectangular, rectangular to parametric. Okay. Now, I like to think of the 2 things I'm going to show you as 2 different techniques, but they're really just one big technique, right? The technique that we're going to use in general is substitution. Okay, so we're going to use either a direct substitution or I'm going to use a substitution with some identities that we learned earlier in class, specifically like the trig identities. So substitution with some identities. We're going to go back and forth between parametric and rectangular. We're going to use direct substitution, and we're going to use substitution with some identities. A little more complex substitution. Still substitution, but we have to remember our trig identities in that case. So let's convert the following parametric equations into rectangular. So what's the rectangular version of this look like? Now here we're going to use direct substitution. And the reason we use direct substitution in this case is because it's really easy to solve for t in one of those equations. All right. So we're going to use direct substitution. So we're going to solve for t. Subtract 5 from both sides. Then divide both sides by 2. And then what am I going to do? Then I'm going to substitute this expression for t in the y equation. And what I'll end up getting is y equals 3 times 1/2 x minus 5/2 squared plus 4 times 1/2 x minus 5/2. And that's it. Now you could simplify that. You could, do the algebra and combine like terms, and I'm just gonna leave it like that for now. Is that all right? I think you guys get the point, hopefully. So direct substitution is just that. I solve for t, or I solve for maybe, if only things use t squared, I could solve for t squared. Or if things just used e to the power or something to the t, you could solve for e to the t. And so solve for t and then replace it in the other equation. So that's direct substitution. I want you to do this on your own. Try to convert x equals t to the third, y equals 5 minus t. And by the way, oftentimes in the book or in the notes, instead of just saying x equals this, they'll put x of t and y of t rather than just x equals and y equals. So they're indicating that x is determined by a function of t. Does that make sense? So that's it. Go ahead and try this one on your own. Now, by the way, actually you can solve both of these for t, right? And not lose anything. So if I wanted to solve for x equals t to the third, I could take the third root of both sides. Typically I don't. Typically, if there's one that's linear, I use the linear one to solve for t. That's kind of my rule of thumb or whatever. If I have a linear one, I'll solve that one for t. But technically, you could solve either for t. But I'll solve y equals 5 minus t for t. So add t to both sides and then subtract y. You get t plus y equals 5, and then t equals 5 minus y. And then substitute for t in the other equation. We get x equals 5 minus y to the third power. Now you could multiply this out and simplify it. I'm not going to, I'm just going to leave it here. Is that all right? So technically we could have solved for either. By the way, it's going to look very different if we solve the other way, isn't it? It's going to look a lot different. But that's going to be all right. You can actually go back and forth between one and the other. Let's do this. Let's go the other way with direct substitution. Let's convert, I don't know, y equals x squared plus 5x plus 7 into parametric using direct substitution. This one's even easier. Okay. What should I let my first equation be? What should I let x equal? Not a trick question. In fact, it's so untricky that it could be anything, right? If you wanted to let x equal 2t, you could let x equals 2t. If you wanted x to be equal to 8t minus 5, you can plug in 8t minus 5. But usually, if we already have something solved for y equals a function of x, the easiest thing to use is x equal to just t. And then we substitute out the x and replace it with just the t. So that's with x equals t. We could have also used direct substitution with x equals, let's just say, 3t plus 1. And then y would everywhere you see an X, we replace it with 3t plus 1. Or we could have used X equals t to the third if I wanted to. And then replaced every X with t to the third. Notice that when we have y equals a function of X, this direct substitution is really, really nice. And again, there are scenarios in which you would want to maybe use a different, what this is called as a parameterization. So there are maybe some scenarios where you want to use X equals t, and there might be another scenario in which you would want to use X equals 2t, or X equals 3t plus 1, or so on and so forth. Depending on the situation. But generally, when I do it, if there's no physical reason to use, no other reason to use something more complicated, I typically just use X equals t. All right? Now, there is, I should say, an exception to that. Here, we already had solved for y. If I have something like this, let's say X plus 8 times the square root of y minus 1 equals 6. This equation is much easier to solve for X. So I'll probably solve this for X by subtracting 8 times the square root of y minus 1. And then I'll let my y be my parameter t. Everybody understand that? It was just a lot simpler to solve for X than it was to solve for Y. Here, we had already solved for Y, so just replaced it. The X with a T, and we're on our way. So in that case, I let Y be T. And again, oftentimes you see this notation, Y of T and then X of T rather than just Y equals and X equals. A lot of times on the board, I just save time by just writing Y equals X equals. But in the book and in Moodle, a lot of it's this. And so what's X? X is equal to 6 minus 8 times the square root of T minus 1. And if somebody else wanted to use 7t, well then just replace the y with a 7t. If somebody else wanted to say y is equal to 9t plus 8, replace the y with a 9t plus 8. So if I can solve for one of the variables in my equation, then I can use direct substitution in a really quick, hopefully efficient manner. And solving for, again, direct substitution going from parametric to rectangular is I solve for t. Going from parametric, or going from rectangular into parametric, I can just solve for either x or y and let the other variable be t. That's pretty easy. Hopefully direct substitution is fairly straightforward and obvious. Now, what about the indirect substitution? Well, the things that we are going to look at for indirect substitution come from our trig identities. And that's the ones we're going to focus on. So, for indirect substitution, or for substitution with trig identities, I'll call it indirect substitution. Recall from last unit that if we have cosine squared of anything plus sine squared of anything, that should give us a 1. If I divide everything by cosine squared, I get 1 plus tangent squared equals secant squared. Now I'm using the t in there because we're in parametric form here. When I originally gave these out, they were all in theta, right? So using t here. If I divide by sine squared, I get cotangent squared of t plus 1 is equal to cosecant squared of t. So let me show you how these work. Let's convert the following equation. Let's do a circle centered at the origin of radius 5. To parametric. And we're going to use substitution with trig identities. Now, there's a couple of different ways you can see this. All right. I'll do this both ways as we are, then we'll do it. I'll do this both ways. So one way you can see this is you can take my equation and divide everything by 25. Divide both sides by 25. If I divide both sides by 25, I get x squared over 25 plus y squared over 25. is equal to 1. Now, this looks very similar to this original Pythagorean identity on trig functions. I'm going to rewrite it that way. I'm going to say, well, this is a single thing squared, x over 5 squared, plus the fraction y over 5 squared, set equal to 1. My trig identity says that if I take cosine squared plus sine squared, it also has to equal 1. Now I wrote it this way so you can see what I'm going to do in the next step. So what we do is we say this is the exact same if you just replace the x over 5 with cosine of t, and y over 5, we replace that with sine of t. So what we do is we simply let x over 5 be equal to cosine of t. And at the same time, y over 5, we set equal to sine of t. This I can solve for x in a very efficient way. This I can solve for y in a very efficient way. Just multiply both sides by 5 in each. So if I let these two be my parametric equations, then the parametric form is x equals 5 times cosine of t, and y equals 5 times the sine of t. That makes sense? Yeah.
The part where it went from x over 25 to x over 5, I'm a bit lost. Was that, why did the 25 turn 5?
So this is x squared, so the numerator squared over the denominator is 25. So if I turn that into a fraction and then square the whole fraction, that means I have to square the numerator and square the denominator. So if I'm just saying 5 squared is the same thing as 25.
I got it.
Yeah.
Thank you.
So this is the main way to do it. This is the way I tend to do it. Okay. Another option you could have done is very, very similar. You could have started with this. You could have said, I think since we're adding things up and getting 25, I'm going to start with this. And then, since I have an equal to 25 on the right-hand side, I could multiply by 25 on both sides. That would give me 25 times cosine squared plus 25 times sine squared equals 25. And then in the same kind of understanding, 25 times cosine squared, I could have taken 5 cosine and squared that whole thing. And then I could have taken 5 times sine and squared that whole thing and got 25. And now this matches my equation. Right? And so I would let x equal 5 cosine of t and let y equal 5 times the sine of t. And all I'm saying there is that in this method, so you get the same parametric, exactly the same. In this method, I took my equation and I made it look very, very similar to the trig identity. This way, I started with my trig identity and I made it look real similar to my equation. And then I do this substitution. Does that make sense? So if you want to start with your equation and manipulate it until it looks like one of the trig identities, that's one option. If you want to start with your trig identity and manipulate it until it looks like your equation, that's another option. I tend to start with my equation and manipulate until it looks like a trig identity. That makes sense. So this is parametric equations converted into rectangular using substitution with the trig identities. All right. Or sometimes I'll refer to that as indirect substitution. Because we're not solving for a variable, we're forcing it to look like something, and then we do the two substitutions at the same time. By the way, that's really kind of an interesting thing, isn't it? This is a parameterization of a circle of radius 5. And these individual pieces actually are pretty easy to deal with. And if you're dealing with calculus and you're taking a derivative, sometimes this is a lot easier to deal with than having two variables that are both being squared. So that's, again, shows you sometimes parametric equations are nice. All right, any questions about this technique so far? We're not quite done with 8687 yet, but these are the basic tenets of it. We'll be graphing a little bit of parametric stuff later, and that's also, we'll use some technology to do that. Hopefully my overhead projector will be working.
So is 8.6 and 8.7 due next week then?
Yes, it's due next week, yeah. Yeah, so the 384 is due this week, the 8786 is due next week. All right, then I will see you later next week.